Good. Okay. Okay, first, thank you very much for the invitation. It's great to be here celebrating Jeremy's birthday. So maybe compared to the other speakers, I got to know Jeremy at a somewhat earlier in my career. So I did my PhD at U of T, not with Jeremy, but he was sort of there the whole time and was always someone I could go to for advice and has sort of been a mentor for me ever since. My first I really understood something about Jeremy as a researcher. Okay, that's maybe not the right way to say this, but so I was at, I think you know, maybe I've been doing probability for 4 or 5 months, and I was at, I don't know, some summer school or something, talking to another couple of graduate students, and they were asking me, you know, what's the probability group like at U of T? And I said, oh, well, there's this, you know, there's this one guy, Jeremy, and then I kind of fumbled on the last name. Maybe it's Costel or I don't know. And then one guy looked at me and said, oh, he's very famous, right? And then the other person nodded along, and that's when I really knew, like, this was, anyways. Okay, I'm going to be talking about, I'm going to be, this was alluded to in a talk, I'm going to be talking about the RSK correspondence. And the talk is 3 limits of RSK. And the end goal is to get to a version of RSK for the directed landscape, which gives essentially a different construct from the directed landscape that doesn't directly go through the area line. So that's the eventual goal. So let's the first part should look hopefully familiar from Amal's talk. So I'm going to start with how I think of RSK. So let's consider a function, m functions from some interval 0 t to Rn. So let's go with this, so f1 all the way down to fn. I'm going to draw them continuously, but they don't really need to be continuous for what I'm going to say. And I'm going to think of these functions as an environment. And in this environment, I can define paths, path lengths, and distances are going to be last pass effective. So suppose I have a path I. So for me, a path I is going to be a function from some interval x1 to 1 up to n, and it's going to be non-increasing. Let me just superimpose a graph of pi on top of functions.
Duncan, the microphone is at a very critical distance from your mouth. Up or down.
I'm a loud speaker, so the question is, I can be extra loud, or maybe I can lose it. Let's pop. I'm not someone who usually needs a microphone, but please let me know if I'm too quiet. Okay, so where was I? You have a function pi from some interval x1 into 1 through n. It's non-increasing, and I'm just going to superimpose its graph on top of these functions. Okay, something like that. And the length of pi with respect to the environment f is just going to be the sum of all of these increments, right? So if I pull this point, say pi n plus 1, pi n. So pi n is going to be the time you jump off of line n. So this would be pi 3, pi 2, pi 1. Then this is just the sum from, say, I equals 1 to n of fi pi I minus fi pi I plus 1. So eventually for us, these functions are going to be Brownian motions, but for now they can be anything you want, right? So think of this as some environment, and this is like the length of your path. And now I'm going to define a last passage value. So let's consider vectors X and Y, which are going to be in the space, we'll call it RK less than or equal to, so this means that the Xi's are increasing, and similarly for the Yi's. And the last passage value from, say, Xn up to Y1 is going to be the maximum over all k tuples of paths I1 up to pi k of the sum from I equals 1 up to k of the length of these pi i's in the environment F. And I need to tell you what set I'm maximizing over. So here the pi I go from the interval xi, yi up to 1 up to n, and these guys are just 1. So usual last passage just involves single points, but from the point of view of the RSK correspondence, it's very useful to define this multi-point last passage privilege. Okay, so here's what the usual RSK correspondence looks like. So this is RSK. It takes one of these functions f and maps it to a pair, which I'm going to call WUF, WRF. And these are defined in the following way. So WUF, which is going to be kind of a more important one for this talk, is just another function from 0t up to Rn. And WRF is going to go from 0t, it's going to go from the interval 1 up to n. Rn. And the rule is the following. So say I want to, I typically define this by looking at the sum of the first I coordinates of WUF at some point x. So this is simply a last passage value from the bottom corner here to the top at location x with exactly k paths. So let me write it. We're going to go to the bottom corner, so I'm going to write that as 0 up to the top part, which is going to be x. Okay, so I'm using this notation xk to just denote a k tuple numbers, all of which are x.
Can you lift the board over the list?
Okay, so I'm gonna take the board back down. Just so I can draw the thing on the picture. So in other words, what you should think of WU as doing is we have this anchor point down here. And we're looking at all either single path or multi-path last passage values up to this top line here. So that's WU, and I call it U because U is horizontal, right? If you're looking at last passage from the bottom to the upper boundary, WR is defined in the exact same way, but going to the right boundary. And here are a few special facts. So there's a bijection. All right. Say you're working with, as long as you have some reasonable function. So if your functions are continuous, then this is a bijection. And as a result of this, it has some very nice so it takes certain nice measures to nice measures. So the good thing, the kind of easiest one to see is say your functions are independent simple random walks. One thing you can note about WU is WU in some sense is ordering. So you have WUF1 is greater or equal WUF2 and so on. So you take, if you start with non-intersecting simple random walks, what you end, if you start with simple random walks independent, what you end up with is non-intersecting simple random walks. Okay, so it has some very nice measure preservation properties. And the other thing it has, and this is something Amal mentioned as well, is it has this isometry. So if I look at a multi-path last passage value across F, going from any point on the bottom to any point on the top, then this is the same as if I do this for WF. And a similar thing that happens for WRF, but like I said, WR is not particularly important for going to the That's kind of gone. You need WR for the number bijection. You need WR for bijection. All right, so are there any questions so far? This is RSK. Yes.
Yeah, I guess maybe it's not so important, but what exactly is WR? It's a function from 1 to 10.
So WR, what you should think of WR as doing is it records rather than last passage values up to the top, it records last passage values to the right boundary. And so because of this, you should think of it as a function from the right boundary, which is just 1 up to n, into Rn. WR is going to disappear very shortly.
Okay.
Old fashioned RSK will be there are random permutations.
Yes, yes. So say I make my paths do the following thing. So every path will have exactly one step going upwards of size 1 and just be flat elsewhere. And the steps will all be at different locations. So basically, you take a permutation and you map it to a collection of paths. Then this recovers the usual RS correspondence for permutations, and your pair WU and WR are the standard young tuple that you get out of that correspondence. So this contains in it these simpler versions of RSK.
You have a notion of young tableau for something like for Java.
Yeah, so you can think of, so you should think of WU as a I mean, you shouldn't think of it that way, but you know, maybe I'll stop right or something. Okay. So what's going to be the idea of today's talk is there's this fact that we're working with a bijection. And the problem here is while this is a bijection, the inverse map is not that nice. So the inverse map is a bit finicky to define. And so therefore hard to take limits of if you want to do something interesting probabilistic. So the strategy for today is we're going to take 3 successive limits of this RSK, where at each stage we can make sense of the inverse map in a really nice way. Okay? And also each of these limits that we take will also take nice measures to nice measures. We'll take nice measures to nice measures and have an isometry property. Which kind of underneath all of this, so I'm not going to say that much about it, this isometry property is what's making everything okay. All right. Well, let's talk about number 1. So rather than working with functions from a finite interval to Rn, I'm going to work with functions from R to Rn. So let me define C of R. I'll just call this F from R to Rn. For now, I'm going to work with continuous functions. And I'm going to assume they have asymptotic slopes. I'm going to call lambda F the limit as t goes to infinity of F of t over t. So I'm assuming that this exists. You don't completely need it, but it's going to be kind of nice to think of these functions as having asymptotic slopes for what I'm going to talk about.
exists in the usual or in the extended sense? Like, can you go to minus something?
No, in the usual sense. So this is just gonna be some number and it should be the same as, it should be the same as t goes to plus infinity and minus infinity. Basically, at a large scale, these functions have slopes.
They can be different for different coordinates.
Different for different coordinates, yeah. So the thing you should be thinking that we're eventually gonna plug in here is Brownian motion with, independent Brownian motions with some drift vector. So when we do this, what should happen with our RSK correspondence? Well, if I take this domain and extend it to all of R, this base point here is going to go up to negative infinity. So that's one thing we should expect. And also, this right boundary is just going to kind of disappear off into the distance and won't matter anymore. So our new RSK map at this level should just involve mapping F to a single system of functions which are called WF. So this is taking the place of WU map. Okay. So now F maps to WF, and again it's going to be in CNR. Okay. So let's assume that so let's write down what WF is. So WF.
I think you need to assume some ordering on the boundary. Correct?
Eventually, I'm gonna get there. Actually, why don't I do it right? Given that you suggested it. Let's assume that you don't need it, but let's assume that ordered in this way. So the rule is going to be my WF just does this. So I just take my function and I plug in this formula that was negative. So I go from a k tuple of points at negative infinity to a k tuple of points at x. And in order to define this, we need to make sense of what this means. So I'm going to write this as the limit as t goes down to negative infinity of f negative t to the kn up to x to the k1, and I need to subtract something off for this to be finite. So I should subtract off a last passage value from the same point, but going to 0.
Not negative.
Yes, one of these things you fixed. So let's try and understand. Okay, so I claim that this is a reasonable definition, and that bijection, nice measure preservation, and isometry all hold here. Okay. So let's start with isometry. You can just check that what we've done preserves the isometry. Okay. For measure preservation, you have the following nice statement. So if B is independent Brownian motions with drift vector lambda in Rn, then WB is also independent Brownian motions, but the drift vector has to change. And so what W does, it has the effect of putting the largest drifts first. The drift vector reading. So, in other words, the drift vector will be first lambda n, then lambda n minus 1, all the way down to lambda. If you're doing this at the level of exactly 2 lines, this is simply Burke's theorem for like a Brownian Burke theorem for 2 Brownian motions. So that thing. Now the really nice thing here is what happens with the inverse map. So this is still almost surely a bijection. when I do this. And the inverse map is very nice.
Is that consistent with before, are they're independent branches? They're non-intersecting. Yeah.
Because we're starting down to negative infinity, they're not non-intersecting. So the non-intersection condition becomes the ordering of the terms. That's the idea.
Before you take the limit, they were non-intersecting, but they went away at different terminal velocities. Now you're focusing where they've gone far away.
But here the lambda has to be ordered, or you have to have this.
Your lambda here doesn't actually need to be ordered. So you could start with your favorite lambda, and W will order that lambda. So that this is the biggest one, then this one, and so on. In the particular case we're looking at, it completely reverses the order. If you started with guys that were already ordered, then W almost surely acts as the identity. So there's this kind of story. Whatever you start with, you order the terms. Yes, two-sided Brownian motions. Yes, everything is going from order.
This is in law, or is it that's a mapping?
I mean, this plane is a mode.
But if they're the same, you said if they're already ordered to begin with.
If they're already ordered, then this actually isn't happening. Almost surely you get what you start with. All right, so now I claim that there's a very nice formula for bijection. For the English, right? So what you can say is that if I let Rf be the following transformation, so I'm just going to take my functions and I'm going to reverse them. Then almost surely RWR of WB gives you back the original Brownian motion B under this. So in other words, to construct inverse RSK, initially, I was doing something like this, right? So I had, maybe I start with 4 Brownian motions with drift 0, 4 with drift 1. To get, in my image, I have 4 with drift 1 sitting above 4 with drift 0. And to go from this side to this side, I do last passage from negative infinity here. And if you think about what this is saying, what I would do to go back is I take this, I reverse it, I do last passage, and I reverse back. Or in other words, I just start at plus infinity, and I do last passage going on. So the map W and its inverse are completely symmetric. They look exactly the same. And so a lot of the difficulty that you had in the finite case with making sense of the inverse map is gone here in our first one.
This is the successive evolution. Successive evolution.
No, it's not. You know, it's a different thing. Yeah.
Presumably the map WR becomes like trivial in this case, you know, when you tell us what WR does, or should we not think about WR?
You should think that it becomes trivial.
Okay, so
Yeah.
in what sense? What's the map?
In a sense that I'm not going to tell you, I can tell you later. But you may already have some sense anyways. But the point is we've gotten two things. We've gotten rid of WR while keeping our nice isometry and measure preservation properties, and we have a very nice bijection. We have a very nice inverse map. So that's the first thought. Now, what can I do with this? So I want to, eventually I want to take a limit to the directed landscape. And the directed landscape involves looking at Brownian last passage percolation across a growing number of Brownian motions. So what I should do is I should take my number of Brownian motions and the setup to infinity. So let's take n to infinity. Now I can do this in various ways. Okay, I'm just going to focus on one of the ways in which you can do this. So let's let B, let these be independent, zero drift Brownian motions. And let's let B tilde be independent theta drift. Brownian motion for theta is some positive number. So what I'm going to do is I'm going to define W theta B in the following way. So this is the limit as n goes to infinity of these finite maps. So I take my finite map W and I apply it to B1 up to Bn and B1 tilde up to Bn tilde. Okay. And I claim that this only depends on B, it doesn't actually depend on what B tilde was. It's only depend on B tilde through the drift vector theta. Okay. So basically I'm taking this picture I have up here, and I'm taking my number of lines to infinity, both in the top part and in the bottom part. And everything plays very nicely when you do this. So what you can imagine that you're going to be doing here is when you take the number of lines to infinity, what you're going to end up with is a representation for W theta B in terms of some last passage across infinitely many Brownian motions going down. Or in other words, you get a Boozman function. So in fact, this is equal to some type of Boozman function. Let me just write it down.
What was the point of having these B tildes? So if the limit you say doesn't depend on them, it just depends on theta. Why not let them be lines?
The reason you start with your B tildes is because when you start with B tildes, you know the output law of W with this guy. You know that the output law is just Brownian motion switched. And so taking n to infinity of law, it's obvious what you get. You just get Brownian motion with a certain flow. But you could, if you wanted to, do it generalized. So this is a Boozman function. So let me write this as a limit as t goes to infinity. Something or other. B negative t, and then there's some particular direction in which you're going to infinity. So it's going to be theta squared t over 2. And this is a k path. Should be a k path movement. And so I equals 1 to k, W theta B I of x. Be this sort of guy. Going to x k of 1 minus the same thing, going to 0 k. All right, so you know that you have, okay, so you have this W theta B, it has this Boozman function representation. You can say, because you knew how the laws were changing at a finite level, you can say that W theta B in law is equal to your original guy B tilde, so it's just independent Brownian motions of drift theta. And your inverse map looks exactly the same as it did up here. So, almost surely, R W theta R of W theta B is equal to B. And you still have, and now it turns out you have an isometry, but the isometry happens at the level of Boozman functions, and I won't go into that so much. The important thing here is this inverse map. So if we want to go, so basically what we've done is we've started with Brownian motions of drift 0. We've produced Brownian motions of drift theta by looking at multipath Boozman functions. And we can go back by also looking at multipath Boozman functions. So I have my Brownian lines. I'm doing these kind of multipath Boozman functions. And I produce drifted lines. And to go back, I do Guzman functions in the opposite direction. And so because of that, I'm going to call this backwards map W negative theta. And there's actually there's another thing that's kind of remarkable about this map. So
Think of W negative theta as being defined in the same way.
you shouldn't think of W negative, you should think of W negative theta as being defined exactly as R W theta. So that's how you make sense of W negative theta. But the notation is suggestive. So now we have a full collection of maps indexed by the real numbers. So in this new setting, rather than just one RSK correspondence, we have a continuum of RSK correspondences. And they have the following thing: for all A, B, and R, almost surely W A plus B is simply the composition of WA and WB, or WB and WA. And in particular, I didn't say this one explicitly, so W0B. Do you have a continuum of RSK correspondences? That's the idea.
Again, is it only in law if you apply it to Brownian motions, or you're saying like you can do it to any?
This, so this is almost surely with respect to the law of the Brownian motions. I mean, in general, you know, if you're starting with something arbitrary and weird, there's no reason for these kind of Gaussian functions to exist. Like the fact that these limits exist, you're using something special. Right. Yeah. But the point is now you have this continuum of RSK correspondences. And they have this remarkable property, which is basically we've defined an R group action. Any questions before we take the final limit? Okay, so the next limit, and I probably have 5 minutes or so, takes you to the directed landscape. So what's the limit we can take now? So previously we had n indexing the number of lines, so we take n to infinity. Now we can't take the number of lines. Doesn't really make sense to increase the number of lines. But we have a new parameter, which is the parameter associated to the RSK correspondence. Okay, so we can try and take this parameter theta to either infinity or negative infinity. And it turns out that when you do this, I'm kind of reverse engineering how we actually talk about this. But it turns out that doing this results in an RSK correspondence for the directed landscape. So let me give a definition.
Maybe in a similar vein, as I'm a little confused. So that you're not defining the correspondence, right? Because the W is not a map on general functions. It's just really a statement about only with respect to these Brownian motions.
Yeah,
right.
So W is, but this is so you could think that each of these W's are almost surely defined for independent Brownian motions. And if you are given some other functions where this definition naturally doesn't make sense, just do whatever you want. You can still define it. You can do it in a measurable way. It's not so important. We only care about Brownian motions here. Yes, okay, actually, this comes in here, right, so they don't have this. No. So, for example, maybe Timo will speak a little bit about this tomorrow, I'm not sure, but all of these, it's not simultaneously true that all these groups of functions will exist, even when K equals 1. So there's going to be a countable set of data where these guys don't exist necessarily.
Does that mean that you can't actually define that? The WAs or all on, like, maybe there's a question of the order of this, where the for all.
Yeah, I was trying to avoid these annoying questions. Let's make it cute. Okay. anyway, I wanted to get to the final thing, so I need to define limit three. So let me give a definition of the directed landscape, which is some change of coordinates version of what Amal put up in his last talk, giving the directed landscape as a limit of Brownian less classical. So let's, for A and R, let BA equal to BAI, I and Z, be an environment. Independent Brownian motions strip A. Let's define some scaling, so I'm going to set X, comma A. I'm going to set X, comma S as scale A to the following thing. So it's X minus A S squared over 4. And then S A cubed over 8. So just some funny scaling. And I'm going to let LA of X S Y T be BA. So this Brownian environment, looking at last passage between XS and YT at this scale A. And then I subtract off something funny. Subtract off constant. So then LA converges in distribution to a 4-parameter field, and this is the directed landscape. So the picture you should have in mind is this. Basically what we've done here, and this is convergence as A goes to negative infinity. So basically what I have is I have my Brownian motions, and this rescaling is kind of, you know, compressing the lines together and shearing the paths. So now they're going to look something like this. And then this guy converges to some limiting object that you should think of in the same way as the last passage like that. So that's the story. So I'll try and be brief if I know I'm just go ahead. Let's just take this directed landscape and attempt to define an RSK correspondence using a kind of Boozman function formula, just like we had here. So define BML, which is going to be a function in the n of R as follows. So the sum I equals 1 to k, bi, I don't know like this, for the L of dil of x is going to be some kind of landscape boosting function. So L going from 0k at negative t up to 0k0 minus L going from 0k x. The limit as x goes to as t goes to 0. So I'm looking at distances to time 0 with potentially multiple paths, and I take the bottom part down here down to infinity. I'm being intentionally vague because I'm a long time. So then BL is an environment of Brownian motion. And what I should be able to say is this is, I'm hoping it's an RSK correspondence, right? So I'm hoping it should be invertible. And it's kind of the limit of all of these maps. And so the question is it invertible? And if so, can I write down an explicit inverse? And it turns out that the answer is yes. So, and if we set these guys BA to be equal to the WA RSK map applied to BL, then. Okay, well, we know LA converges in probability to the directed landscape as A goes to negative infinity, but we can actually do better. We know that LA converges in distribution to L. Okay, kind of gave away a bunch of language. We can do better and say that it actually converges in probability. So under this funny coupling through all these RSK correspondences, you recover the directed landscape as a measurable function of infinitely many independent Brownian. Okay, so that's. Okay, so there's a couple of problems that you could take there. So one thing you could ask would be to make this convergence quantitative. I believe there's a way you can do that. And that gives like then you should be able to get some quantitative estimate on how far your Brownian defined environments LA are from your actual directed landscape. Or maybe I'll say our bigger hope was that this gives a way of constructing the directed landscape that removes the airy line ensemble and just relies on simpler objects, so stationary measures. So just Brownian motions. And so hopefully you should be able to get some softer ways to prove convergence. But of course, there's also some big RSK machinery.
Yeah.
Does it make any sense to put A to positive infinity?
Yeah, it does. Everything works in the same way. What the negative infinity was arbitrary. It's just because that's the way we're. Maybe I should say that the paper is hopefully going to be on the archive in a couple weeks. It was one of my goals before the conference to post it.
You do get the directed landscape.
You still get the directed landscape. A to negative infinity, A to positive infinity are like symmetric. They're very natural.
Comments?
I have a rather basic question for the first one. Well, I understand why if you make the drifts ordered, why it kind of means that they're independent, there's no non-intersection. But why if you make the drifts equal, are they going to be be like independent without any non-intersection?
If you make all of these drifts equal, then your map isn't doing anything whatsoever. So you should think of for a mix of some equal slopes and some unequal slopes, what you should think that this map is doing is it's occasionally, so if you think of sorting in terms of Pitman transports, that's how we do this in practice. What's happening is occasionally you're doing an actual Brownian vert type theorem. And some of the time you're doing absolutely nothing.
Thank you.